My name is Akshay Pawar. I'm a senior tunnel engineer at GeoConsult India, and I'm also vice chair of TAIym. Today we have the privilege of having one of the distinguished speakers in the field of tunneling among us, who will present this webinar, Mr. Russell Brown. Although he needs no introduction, I'll give a short brief to you. He has over 35 years of experience in the field of tunneling. He has worked almost throughout the globe in all European and non-European countries like Egypt and India, Hong Kong, etc. His experience range is quite vast, right from hand-mined excavation to hyperbaric working to Cajun sinking, to all the modern tunneling method, different types of TBM, drill and blast methods. So he is a very apt person to speak to the young engineers about tunneling. His association with India is more than a decade long. He has been associated greatly with Bangalore Metro to Chenali Tunnel, and right now he is with L&T as their tunnel technical director for their TBM Academy in Kanchipuram. Today's topic is should be a great interest to all of us, especially young engineers, because it is about underwater tunneling. He will be talking about the project he was involved, which is Tideway Central Tunnel in Tideway Central section of Thames Tideway Tunnel in central London. This is a $6 billion project, which is a 25-kilometer long tunnel which collects the rainwater and the surface sewage and convey it. Why I say it should be of a great interest to us, because in India we don't have much experience of underwater tunneling or under river tunneling, should I say. And especially in northeast and the eastern part of India, there are many projects which are coming up where such experience is required. So we should grasp whatever we can from him today. Without taking more time, I will hand over to Russell. Russell, please take over.
Okay, hi, thank you for that, and good morning, everybody. Okay.
Good morning, sir.
Yeah, thank you. I'm just gonna two things I'll just point out before I start. One, you can hear me very clearly, yes?
Yes.
Okay.
Yes.
Two things. One is there seems to have been an electrical issue here, and some of the electricity is turned off, so they may swap from generator back to mains power. When they do, I may get a problem. So if we do and we have to stop for a few minutes, please bear with me, and it means I'm waiting for it to boot back in, or I can go to my mobile and put it in hotspot to my laptop. So if that happens, please bear with me. And the second one is, I live in an apartment, and sometime during the day they come and knock on the door and ask if I'm okay. So because of the present circumstances with the virus, so if I have to stop and go away for 20 seconds, then I'll come back. So sorry about that. We'll just have to bear with that. They come round and ask, are you okay? Okay. And thank you for the introduction there. But very quickly, I'll kind of introduce myself and hope I don't go too much of what was said a little bit earlier. My name's Russell Brown. I've been now with L&T for the second time. My employment with L&T for just over 1 year now. It's almost anniversary back with L&T. I came back because of a particularly nice offer to look after the academy, of which I'd been back in the UK, so I've been back about a year, just over a year, and I went back to the UK for about a year and a half, 2 years approximately, I apologise, on Tideway. And then before that, I'd worked for L&T for 2 years as more of like a tunnelling advisor level, and advising working procurement teams and execution teams on all kind of varied projects, where I did the technical reviews and chose the 2 TBMs for Mumbai Metro, the 2 Robbins machines, which I don't know if any of you get the Tunnels and Tunnelling, the June edition. I got an email this morning, and there's a very good write-up for, I don't know if anybody's seen it yet, fantastic write-up from Robbins. I think it's Robbins particularly who's wrote it on the 2 Robbins machines in Mumbai Metro. So and last month, the May edition in Tunnels and Tunnelling, we were also in there again. So that's 2 months running is quite good. So yeah, going back to my very early career since leaving university in the late 80s, I was a graduate engineer for a company called TAIym, and I was in the heavy civils department, which was, I did like the deep excavations and basically building sewerage works, deep excavations, and kind of excited me. And with that kind of work, as I got involved in tunnelling, because between these deep excavations there used to be small pipe jacking and things like that happening. And so I got involved as a young site engineer, not knowing anything about this. And sorry, I'm just going to point something out. In them days, if we wanted to do a tunnel, and it's quite interesting exactly what you're saying about new techniques, but I started for 2 or 3 years in very old traditional techniques, and then saw the mechanization within a few months of seeing it, but then working with it for 2 or 3 years until I saw it change. When I first started in tunnelling, we used to put a shaft down by caissons. Diaphragm walling certainly wouldn't happen, so it was sheet piling, caissons, underpinning, so we used to jack the caissons down, normally with tunnel segment rings. What we used to do, we'd put 2 shafts down, and then we'd put a steel cofferdam, excavate this cofferdam out, maybe about 15-20 meters long, depending on the diameter of the tunnel we were doing. Now, this is only to go 100 meters, remember. We do that nowadays in two or 3 weeks, to put a 2.5 meter tunnel down. And we would put a small hand machine down there, build some segments, put lock doors in, backfill it, put compressed air on, drive the tunnel. That'd take us 2 or 3 months to do that. Then we drive across 100 meters. And then what we'd have to do is pull the hand shield out. It was all done by hand, all in compressed air. And then we'd have to line the tunnel, because many years ago, the rings had these indentations in them. The bolts were put in straight across. There's no curved bolts or spear bolts as we see now. So they had these indentations in, so you could put the bolts in. And then you'd have to line the tunnels with the kind of traditional like ribbon laggings. And that would doing very well without any problems. That would 6-7 months. Now nowadays we'd probably take 2 or 3 weeks to set a pipe jacking machine up, and 2 weeks to put the pipes across, and it's finished work. So it was quite interesting to see that. And if I'm honest, it taught me a lot of invaluable information about traditional techniques. So after that, I joined a company called Lilies in Cairo, again as a young engineer out in Egypt, and we were building about 5 meter diameter tunnels, many kilometers, with what was in them days very state of the art Surrey tunnel-boring machines. And in fact, the company we worked for, one of the first things they said to me was that I must learn how to drive a tunnel boring machine and learn how to drive the slurry treatment plant. A lot of these machines need 2 drivers. So I learned how to drive the slurry plants, how to manage the treatment process, the slurry mud technology, and look at how you can process, to know if the slurry treatment plants are efficient in taking out the fines and the solids, and then go into tertiary treatment. And in them days we had belt presses. Nowadays we use a lot of centrifuges and filter presses. And then after that, I kind of worked, my superiors there were all kind of very, and some of them still are, very senior people in tunnelling. A guy called Alistair Bigart was my boss. Certainly he's coming to the end, but he writes many papers. He's a real authority on tunnelling, a very well respected person. I'm sure maybe some of you might have heard of Alistair. And he then became very senior on the Channel Tunnel. So it was kind of, we got the job in Egypt, then it was on the Channel Tunnel. So we went on there, and I got a pretty senior position in kind of managing, as a senior engineer, managing one of the tunnels, the first one to break through. And it was my methodology where we learned how to, where the French were by drilling a special probe, what we could survey, and we found out where the French were, so we could then, we could then match up underground. So I developed that system, and then remember being under a load of pressure, going to a directors meeting, and they all telling me my method wouldn't work, but I stood by it, and in the end, it worked. So first time hit the TAIym on the French side, which was 120 meters away, which is very difficult when you know the drill's deflecting and pulling to the right. And maybe that's another paper we can do another time, but very interesting. And then after that, just after that, I joined a Japanese company in the UK, Nishimatsu, and we did a joint venture with Taylor Woodrow. Probably not many of you would know Taylor Woodrow Tunnelling now, but they came out of tunnelling a few years ago, and now they've set up their own consultancy, completely separate of Taylor Woodrow, and a very good tunnelling consultancy. And if anybody, particularly for hiring out very good staff, if you're looking for supervision and things like that, and they've now got their own consultant. It's called London Bridge Associates, which is ex Taylor Woodrow Tunnelling. So I'm sure some of you might have heard of London Bridge Associates. So I did that for a few years. After that, I went to Hong Kong with Caverna Cement, but it was Trafalgar House Cementation when I joined them. Within about 6 months, it was Caverna Cementation, and I stayed with them for 5 years in Hong Kong. We did hard rock TBMs, called the SSD sewerage. Now we're talking about underwater tunnelling, and we were 160 meters underground in quite hard granite, but with many decomposed granite areas, and drilling and grouting to stop 16 bar pressure. The initial contractor was Campion Bernard Maeda, a French Japanese company. I'm sure a lot of you might have heard Maeda, maybe not so much Campion Bernard. But their contract got determined because they were not stopping the water. So we took it over, and I was a PM then on these 2 hard rock TBMs, where to be honest, what we did, we took over, and it was obviously, my role there really was to set up effective drilling and grouting of rock at stopping 16 bar pressure, using a mixture of OPC sometimes, rather than the expensive microfines and ultrafines. And I would use them once the OPC had kind of done its job, and filled out most of the, stopped most of the water, and then we would use the expensive materials to really make the tunnel dry. So that was a very good exercise. I was a PM, but if I'm honest, my main function was to keep the tunnels dry, and that gave us a fast production. It was quite easy tunnelling, but obviously it wouldn't have been if we had to stop the water. So I've got this experience of pressurized TBMs, and obviously then free air tunnelling, hard rock TBMs, particularly, and then ground improvement in rock. So what I'm in Hong Kong. Yeah, then after that I came back and worked in Dublin, the Dublin Port Tunnel, where we had two 12 meter internal diameter TBMs. We knew at the time when we built those TBMs that actually, from a design point of view, the legislation had changed, where really they had to be 14 meters, and we agreed with Dublin Council that Dublin Port Authority, should I say, that because when we'd done the design and tendered the project, the road tunnels design had changed, where you need the you need the slab and the ventilation at the top, so we could keep it 2 meters diameter shorter. And not just that, in fact, if you do some historical reading on that, you'll see there was criticism for only putting in 12-meter tunnels. It should have been 14 meters. But if you look back, it would have meant we'd have to change most of the bridges from Dublin in Ireland all the way up to Belfast, which I think is about 150 miles, to over 200 kilometres anyway. So that was another reason for not needing to make them bigger. And then after that, just shortly after that, it took around about 2010, I came to India with CEC, one of my ex-bosses when I worked in Egypt, a guy called Bob Moncrief, some of you may know. He was working in Delhi in the very first phases, 2008, something like that. So I came to India with CEC, Bangalore Metro, which has been very interesting because we had very good machines, and we knew in Bangalore Metro we had the Hitachi machines, what we call the conventional Japanese style design, where you've only got one excavation chamber. And what I mean by that with the Surrey machine is what we call the Western type design Surrey machines have a secondary chamber which has an air cushion bubbling, so the air pressure is helping to stabilize the face pressure. And it's very important when you've got very low cover and you need that very, very fine earth pressure balance control. They were originally developed, those air bubble plenum chamber type machines, for very low cover. I remember them coming out many years ago, very low cover, originally 2.5 meter machines with a plenum chamber, so you didn't get bursting or slurry on the surface. So we had the Hitachi single machine in Bangalore, and in fact the only problem really was where for our cutters we had I don't want to talk about costs and things like that, because obviously I work for L&T and we've got a second phase 2, so it wouldn't be right of me to talk about monies and what we're doing and what we did and how we've improved things to some degrees. But certainly we had a huge amount of money, many millions of dollars for roller cutters, and we spent about 80% of that, so we got it right. But the time, I've got maybe one day when it's correct. I think that would be a very interesting paper, because I've got records to show where we did one drive from in front of Vidhana Sudha in Bangalore, if anybody knows the area, where we did 80 interventions with 1 TBM over just under 1 kilometre. So that was 160 interventions with 2 TBMs. The big problem there really was the cutter disc wearing out, but not on diameter, wearing out and sharpening. So that's been interesting because of being able, getting all the knowledge on the TBMs were powerful enough, there was no problems. In mixed face ground technology, mixed face ground tunneling, should I say, the problem is over excavation. It's very difficult not to over excavate, even with all kind of machines. I mean, one could argue our variable density machines are right machines for Bangalore. That maybe that's a question. I've certainly thought about it. But what I've done is I improved the Bangalore machines by working back with L&T and choosing these 4 machines we've just gone for Bangalore Metro. And I've looked at improvements, and the only improvements I could make was really making the cutter discs, instead of we had 17 on phase 1, making them to 19-inch cutters and making the airlocks bigger.
Russell, Hi, Russell. Sorry to interrupt, but could you share your screen as well, because we are not getting the video.
Okay, I'm going to start the video now. It was just a quick introduction to India, and I'm joining L&T. So what I'm
sorry.
That was just a general introduction. Okay. Cool. So that's where we are really up to date, and so what I'll do, I'll now start this presentation for Thames Tideway, and if you just give me 10 seconds while I load that up. So what I'd like to ask, by the way, first of all, can you all see the video? And I've got it moving. Can you see the screen?
Yeah, we can see now, sir.
Okay. So what we'll do is Thames Tideway project. I was there for just under 2 years, something like that. And what I'm going to talk about is whilst I was there, we purchased 2 tunnel boring machines. The internal diameter of the segments was 7.8. The TBMs were about 8.4, something like that. So the ID of the rings was 7.8. But later on, once the tunnelling had finished, they had to be lined with a secondary lining down to 7.2. And that was for long-term durability, for the 125 years design life, and for some of the pressures from the vortexes pushing the water down, the overflow chambers. It's basically a stormwater over retention tank, 25 kilometres long, and I'll show you the layout in a second. I was involved in the central section, which had 2 drives, one a west drive with approximately 5 kilometres, and an eastbound drive going down the Thames. And in fact, on this slide you'll see here, we've got Tower Bridge. These works were part of the central section works, and I'll show you the layout in 1 second. So okay, this is where we started, and just to get your bearings, this is just off the picture is what they call Battersea Power Station. And I went in there on a visit, quite amazing history in there. And, but again, another paper. Now, what I want to say, this is one of our mucking bays we developed. And this is a site here. You see the segments, the segment barges, conveyors coming to barges, and barges parking up, and the shaft is in here. What I want to point out is that whilst we were flow, which is Ferruvial Lang or Rock, we also had another project which was here. Now this is a station for Battersea Power Station for the Northern Line extension. So we also had this street here is called Kirtland Street, and I'd forget what this name is. I forget what it is, this street here. But Battersea Power Station development was happening, building. The idea, all this is going to be expensive apartments, and you'd be lucky nowadays to buy one for $1.5 million US. That's probably about the cheapest you could buy one for. So all this power station was being turned into apartments. You got the Northern Line extension, 2 TBMs, and then the Tideway extension here. This street here must have been, this Kirtland Street must have been the busiest street in Europe for. Probably still is, actually. There's so much construction going on here. You can imagine the issues with that. Now, the Northern Line here, which was flow as well, by the way, remember, where we were able to utilise some of the equipment off them. Because of knowing the problems around this area, very clearly in our contract it was very much stated, very bluntly, everything by river, everything. And obviously, if we wanted any bulk deliveries of without going into details maybe, we had to prove that there was a good reason it didn't have to come by river. And the reason for that was just up here, literally, if you go about 1 kilometre up here, up this street heading this way, I think you can see my cursor moving. Yes, by the way, it's helpful because sometimes I'm pointing.
Yeah, we can see.
Yeah. Just up here is the new American embassy, massive big place, and it's next to an area called Vauxhall. And Vauxhall is kind of the area where it's right on the outskirts of London. When I say the outskirts of London, it's central London, but what we would call on the outskirts of the city itself. Westminster, the Big Ben, that's all just up here. So it's you get right into the city centre of London very quickly here, and it's very busy. So there has been lots of problems with trucks. There's a lot of infrastructure in London to put in these cycle highways for pedestrians, go on the bikes, and there's a big thing where you can pick up free bikes, and they're everywhere. There's these free bikes. They just park up, and you put your credit card in, and it lets you take them out, and they put them back, and you don't get charged. So there's lots of accidents and people getting killed. So Transport for London, who's one of the obviously main stakeholders in us working and getting permits for all kind of things, stipulated everything had to be by river. So there were lots of things came by river, cement, segments, and the spoil, obviously the big one. So we had to spend a lot of money on the development of conveyors and things like that. So that's just kind of where we are. So in plan view, that was Kirtland Street we're just looking at, and the one tunnel came west towards Carnworth Road. Now that has actually finished and did amazingly successful, no problems. Now the other tunnel is just under 8 kilometres to drive to this Chambers Wharf here. Now at the moment it's parked up here at a place called Blackfriars. And it's done about half of its distance, and now that also, by the way, is the tunnel which we started second. And the reason we started the second tunnel, which was the longest drive second, was because this tunnel here we always knew was the easy tunnel for sake of ground conditions, but we had to cross within about 600-700 meters of launching off this tunnel. We had to pass under another tunnel, which is what they call the Water Ring Main in London. So there's a tunnel under London now. I think it must be about 10 or 15 kilometer diameter. Yeah, it's about a 4 meter diameter tunnel, but it goes around London, and it probably have a diameter of 15, 16, 20 kilometres, something like that. It's all over London. And it's basically got water, fresh water, drinking water in it, pressurised water. So all around London, drinking water can be moved around dependent on many factors, maintenance, bursts. So it's a massive big tunnel project, what was done in the mid-90s actually, and it was one of the biggest tunnelling projects at the time. Massive. You can imagine how many kilometres, 30, you probably, as I say, 70, 80, 90 kilometres of tunnelling. Massive project. We had to travel under this water main, and we had a very short period of which to do that, where they looked at water demand over the year and said, look, we'll give you this very short window of opportunity to get underneath it. And obviously, because we're very deep in the zone of influence, we had a very long drive. We were approximately maximum 60 meters underground. So we had to get under this zone of influence very quickly. And we were coming to our zone of opportunity to get under this tunnel. So we sent this one off first, which it was never the plan. The plan was to send the east tunnel off because it was the longest drive, but it was better to send this off because of that issue. That's why that went first. Anyway, we launched the east drive, and it's now in Blackfriars, parked up. One of the things, and I left it obviously before it got there. And one of the things we always planned was the TAIym would get there, and then we would do a large amount of refurbishment. Now, dependent on the programme of Blackfriars, and there were potentially many issues there with the excavation in respect to being able to do it because of a big problem with an existing gas main, what was causing many problems. They couldn't move it because it would have cut London off, a huge part of Lambeth and Southwark and Westminster of gas. So we had to work around. It was very, very difficult. So the TAIym, I know for a fact, just checked this morning, it's parked there and it's doing a refurbishment, changing. What my plan was, and I'm sure they've done the same, is to change all the tail seals, put brand new tail seals on, obviously do the cut ahead, and because as you leave Blackfriars, you then quickly come within about 1 kilometre. So there's about another 4 kilometres left to go here, approximately. As soon as you leave here, there is, after 1 kilometre, there is, you get into sand. So the TAIym will hit Thanet sands in the bottom. Then it will go through the Thanet sands, which is a full face of sand. And then, so it goes through the Thanet sands for about 1.5 kilometres. And then it then migrates down into the chalk. And so down, and then it will go then into a full face of chalk. And by the time it gets to Chambers Wharf, it'll come to a full face of chalk. So this latter half here will prove very interesting, because it's an Epb machine which is going to go into a full face of sand. Now we're not, we don't need to, there's it's not something which is ideal, but there's some quite unique Thanet sands. They're kind of very cemented, very, very dense sands. So by adding polymers, we would have expected to get through it. But I think the next 3 or 4 months, you should start to see interesting stories coming from this latter part of this when they start getting into this. It could, good luck to them, and hope all our planning, what we did, and the machine we chose, very difficult to pick a machine what's predominantly got to go in clay and then go into sand. The chalk won't be a problem for it, although chalk is very, very can have high permeability and can be quite abrasive with the flint. Chalk's not abrasive, but the flint is. But we don't expect too many problems. At least there's no fines in it, but it'd be interesting to see this section here near Tower Bridge, this famous landmark in London where all the sand is. So interesting stuff. Down at the bottom are some, these are not my words, by the way, put on record. These are estimations of the initial price and what may be the end up price. I think the current price for Central is about 750 million, which would be $1 billion US, approximately 1.2. The exchange rate is something like that now. Times any of these numbers by 93. So if you times 950 by 93 would give you the in rupees. Okay. So just a quick overview of the project and a general overview. Tideway is the largest water infrastructure project currently under construction in the UK and will modernise London's major sewerage system, the backbone of which dates back to Victorian times, although the sewers built in the mid-19th century are still in excellent structural condition. The hydraulic capacity was designed by Sir Joseph Bazalgette for a population and associated development of 4 million people, where it's 4 or 5 times, 3 or 4 times that now. Continued development and population growth result in the capacities of the sewer system being exceeded, so that when it rains, there are combined sewer overflows to the tidal Thames performing as planned by Bazalgette. So when it rains, all the sewers are overflowing into the River Thames. To reduce river pollution, risk to use of the river, and meet bespoke dissolved oxygen standards to protect marine wildlife, discharges from these CSOs must be reduced. The Environment Agency has determined that building the Tideway tunnel combination with the already completed Lee tunnel, that is another tunnel which is at the end of this Thames Tideway, which picks up another. The Tideway tunnel connects into the Lee tunnel, and the Lee tunnel is farther east. That picks up a lot of the sewerage from east of London and takes it to a place called Beckton on the on the east side of London, where massive sewerage works have been built and improved. The sewerage works in London themselves, in the city centre, there's no room for upgrading them at all. They're just in a restricted area, and there's no room for building more, settlement ponds and things like that. Okay, the Thames Tideway Tunnel closely follows the route of the river, intersected by sea zones, and the discharge is 18 million cubic metres of untreated sewage a year. Once completed, we say it will connect to the Lee Tunnel, and sewage will go to the Beckton Storm Treatment Works. Due to the size and complexity of the project, a new wastewater utility was formed, Bazalgette. That's a Bazalgette Tunnel Limited. Those are the owner of the present Thames Tideway Tunnel. So it's not done by the utility company in that area is Thames Water, but this private company, Bazalgette Tunnel Limited, training as Tideway, formed a company to build this. So it's the moment it's all private funded. Tideway, there's some money from Thames, by the way, but it's generally private funded. Tideway will construct, own and maintain the Tideway Tunnel. However, Thames Water will remain the overall operator of the sewerage system. That includes the tunnels. Tideway has split the project into 3 detailed design and construction contracts, west, central and east, of which we're going to be talking about central, which roughly corresponds to 3 distinct geological zones encountered by the main tunnel. There is also a 4th overreaching systems integrator contract providing the project's monitoring and control systems. Jacobs Engineering is the overall program manager for Tideway. The 3 civil works contracts were awarded in 2015, and the program is for all contracts to be sufficiently completed to allow commissioning by 2022, with handover and CSO control by 2024. Following handovers, an 18 to 36 month system acceptance period, for which at the end Thames Water will take over maintenance responsibilities for the near ground intersection structures and assets. And basically it's an 120-year design life. Key elements of the contract. This presentation covers a central contract, which was an initial tender value of £750 million, times it by 92, 93 will give you in rupees, or 1.2, so it's approximately $1 billion US, is the largest of the 3 area contracts, which is JV between Ferrovial Agreement, a Spanish company, and Langor Roque Construction, which is a UK company. It's the main contractor, and they've appointed TAIym as main designer for the permanent works to provide the detailed hydraulic, civil, structural, mica and architectural design. I'm going to kind of executively go through this rather than reading every word. Main tunneling activity is focused around the Kirtland Street site adjacent to Battersea Power Station, where 2 TBMs will drive out the shaft for a distance of 5 kilometres on the west to get to Carnworth Road in Hammersmith and Fulham, adjacent to Wandsworth Bridge, and 1 driving just under 8 kilometres easterly to go under Tower Bridge to meet the east contractor, which is Vinci and Costains at Chambers Wharf in Southwark. The west contractor is Morrison's. In addition to the main TBN launch chamber, there are many offline shafts, and on the central tunnel there's a further 7 shafts, and the other 7 shafts are all vortex chambers to connect from the high level sewers to vortex to drop the water down into the main tunnel drives. Interestingly, the Kirtland Street drive shaft, which you see and we'll talk about, that shaft will actually be capped off and concreted up because it's in such a prime location, and it's not under the Thames, obviously, it's to one side. It's probably about 20 metres off the riverbank. There's such that land is worth so much money that they have to give that they can't get it, so they've got to hand it back, otherwise a loss at development. And the other thing is there is no large volume sewer nearby where anything could be connected into. So the Kirtland Street shaft, the main drive shaft, is redundant, and basically it'd be there's all very, very expensive apartment blocks going around there, particularly, as I say, because you've got a new American embassy at the side of it, so around that area it's kind of a new up and coming smart part of London, and you've got a brand new station, the Northern Line extension, so it's you know, people are paying £500,000 less for apartments even though they're expensive, so it's a nice place to go and live. Okay, key drivers and design challenges. While the west contract of the main tunnel is predominantly in London clay and the east contractors are in chalk, the central section covers a range of ground conditions with sands and gravels forming major constituents. And we kind of spoke about that, and we'll look at a general layout later. So I don't really want to go much into this page, but it's there for your reading later if you'd like to. So I'll move on to the next page. So this is Kirtland Street. So you've got this 5-kilometre drive going uphill towards Carnworth Road, because the sewerage works. This is Abbey Mills pumping station here. Drops water into here. Excuse me. This connects into the Lee Tunnel. So about 6, 7, 8 kilometres past this shaft here is the Beckton sewerage works. So all this is gravity flow down to that. This is a central section in green here, Kirtland Street. There are, in between Carnworth and Chambers, I think there's something like 2 shafts this side and 4 this side, what we connect into, for dropping the water down into the central section. You'll see some of those in a second. I'll show you actually, when you look at all these, it's predominantly clay. This is a very good solid London clay here. Now it says sand and gravel here. It's this, a lot of this area here up to about here is predominantly very, very high clay content. It's not what I'd describe as sand and gravel. I couldn't actually find if you like, a presentable section through, and I'll show you a picture of the face in a minute, by the way. So you've got predominantly clay and sand and gravel pockets up to about here, and then it goes into the sand and gravel, and then you get into the chalk. The chalk's about 1 kilometre back from here. Then you've got the Thanet sands, which is just pure sands, and then you've got a mixture of sand and gravel and high volume of clay up to about here. And then predominantly up here, it's very, very clayey material with inclusions of sand lenses. And from memory as well, and obviously they've got through it okay, there was a sand lens at the top of the TAIym. I've worked in London before, and you can actually get sand pockets, and we did a station excavation in Farringdon a few years ago for Crossrail, where underground we had to dewater the sand lenses and then inject them with sodium colloidal silicate, to solidify it, so we could build the cavern underground for station. That was a Crossrail project. Okay, this is a typical picture of what they say is kind of sand and gravel, so it's just a very general notation. But this is typically what we found when we did these caverns to launch the TBMs. You've got this very stiff London clay up here, the upper mottle beds as it's called. Then you've got the lower Thanet beds, and there's all different. When you look at these, there's all kind of river deposit shells, all kind of things. This was a concern for us. These sand lenses here, not because there's water in them, they were very, very strong and very strong lenses, very compacted lenses where, in fact, I ended up putting more roller cutters on the TBM because I think they would have damaged the scrapers. Some very, very hard lenses. And the trouble is, we didn't know how far these could go. They could go the full length or just stop after a few hundred meters. They can undulate, so it's very difficult to know where they are. And then here you kind of got gravel beds, And then below here, you would get this stannic sand for maybe 10, 15, 20 meters thick. And then below that, you'd get the chalk. London is basically built on clay, overlying chalk. And then obviously you get different zones of that for about 15, 20 meters. Then you'll get this transition from very solid London clay all the way down to the sand. So you get different kind of mixtures as it's coming down. London is lots of water. It gets pumped out of the ground, as it does in a lot of countries, for private use, for factories, for all kind of uses. And what's interesting, by the way, that London's water levels are rising by something up to nearly 1 meter a year, and it sounds an enormous amount. And it's been happening for apparently speeded up in the last few years, and it's through industry not pumping water out the ground and whatever the whole reasons are. And because we looked at this, as we do as civil engineers, we look at these things to see if there's a claim situation there, because of more water since we tendered the project to when we did it. A rise of 2 or 3, 4 meters puts more pressure on the TAIym head, kind of slows the TAIym down. Should I say, not from a claim situation, from a technical situation, we looked at it to see, had any of our designs would have differed massively to what we were looking at in them days to what we ended up doing. And we'd allowed for it, but it's just an exercise we did. Can I just say, when I had to set up with these TAIyms, were working, when you're working in hyperbaric instances in compressed air up to 3.5 bar, just to give you very quickly, in compressed air, approximately you can work in up to about, I'm going to simplify, you can work in compressed air up to about 10 hours. Okay, below 3.5 bar I'm talking. Now 10 hours means also the decompression times. Now at 3.5 bar, you're decompressing for 343 minutes exactly. So that's what, 6, 12, 18, 36. So you're decompressing for, say, nearly 4 hours. That means you can work in 3.5 bar for nearly 6 hours. I think it's about 5 hours, something like that. 6, 12, 24. No, for nearly 5 hours. I do apologise. So what you're doing is you're allowed, I think, 3.5 hours working, and you've got to decompress for nearly 5. So that's kind of your 9 to 10 hours maximum period. So your exposure time is less and your decompression time is longer. So we're having to look at that in London. And as you come down to 1 bar, for example, or below 0.7 bar nowadays for oxygen decompression levels, you can probably work for something like 8 hours and only decompress for 1 hour. So it obviously, as expected, it would depend what level you're working at. Because we were going to be over 3.5 bar, what it meant, for those, I'll just kind of, what that means is we were going to have to look at working in mixed gases. So that means that you can't breathe the normal compressed air. It meant you had to breathe with like a motorcycle helmet type diver's mask, not a mask, a helmet with piped air, where you're breathing either compressed air and a mixture of helium gas. What I chose with the compressed air, our compressed air specialist lock keeping medical organisation. Forget the name. I do apologize. He'd go mad if he knows. I can't remember the company's name. But what we chose was compressed air, helium, and nitrogen. That's called trimix. And we looked at doing that. So people over 3.5 bar could enter these with this mask on, breathing mixed gases. So we set that up on these TBMs because we could easily go above 3.5 bar. So it became very, very hard, very hazardous kind of working. And and something we had to do a lot of planning on. Okay, there's some other information here. It's just there for backup information. I'll just read the executive bit on this something, I think. The TBMs are supplied by French contractor NFM Technologies, and they each got approximately, the TBMs weighed approximately just over 700, just under 800 tons, and all the TBMs are approximately 100 meters long, and we used conveyors with vertical conveyors leading out to surface works to either go on a stockyard or go straight onto barges. So that's kind of long introduction, but we'll quickly show you some pictures now. You can get a better understanding of the project. So this is a central section. This is Kirtland Street. So we had so got the Kirtland Street. We had 1, 2, 3 shafts, CSOs picking up sewerage on this side. So sewerage, this was under the central section because the TBMs broke out at Carnworth Road. So you got 3 on this side, and then we had 3 on this side. Can I tell you, the 4th one, this Blackfriars Bridge, was also a vortex shaft. We actually looked at missing the TBM altogether and driving around this, but it was very difficult to. This had a huge amount of water what dropped down this shaft, and we couldn't design the cross passage to handle that flow. And the other thing, which my particular effort along, dealing with all the joint venture, was to say, look, we need to park the TBM in here to refurbish it, because this short length here is very risky soil because of the sands. So we need to change all the. We need to refurbish it very, very to a high level, to a new level. Put new tail seals and new cutter discs. Okay, so Thames Tideway Tunnel. We had the West Drive, which had an aspect opening ratio of 50%. It was a lot easier clay, a lot of easy digging. That's me there, by the way, at the factory acceptance test in Le Creusot in France. And then the East Drive had a smaller opening aspect ratio because of the less clay, more sand material. And it was obviously designed from NFM, and we agreed everything. So these are the 2 main project managers for NFM. That's myself, and we went there and did the fat tests. This company now, NFM, it's the French company. They at the time they were building the TBMs, we realised there was something going amiss with the manufacturing, and we had lots of suspicions. There were some problems, and they eventually told us that they were probably going into receivership, and they did that. They were owned by a Chinese company at the time who basically pulled funding and left them a bit of an issue. So they've now been brought over by another tunnelling supply company called Mulhauser. Mulhauser supply locomotives from rolling stock. I'm sure most of you may have heard of Mulhauser. That's now who owns NFM, and I hope they keep going, because they're a fantastic engineering TBM manufacturing organisation. And they, let me think, apart from BSAC, which is another French company, what does bespoke type TBMs, and I advise you, if you need anything quite specialist and short length and some real innovative design, BSAC are the one we would go to, and I advise you, if you want anything bespoke and quite difficult, BSAC are a company to talk to. And NFM, I'm sure at the moment they're still going, but I don't know how long that'll be. Okay, I just want to show you this scheme video, what we produced, and I think I put the I'll tell you, I'm just going to come out and put the audio for you to listen to. I do apologise. I don't think I pressed that button. Just 1 second. Just going to reboot this up. There we go. Hold on. Include. Excuse me. I don't think I did it. Just a minute. There we go. Can you hear the audio, by the way, when it's playing?
Yes, sir, it's audible.
Okay. You can hear that.
Kirtland Street is key to the success of the central section of the Thames Tideway tunnel. It's the primary worksite for this contract, and it's here that the main tunnels commence their respective journeys to the east and west. The site is also right at the very heart of the 9 Elms on the South Bank regeneration programme, currently the largest of its kind in Europe. The Ferrovial Laing-O'Rourke joint venture understand the concerns and aspirations of the many stakeholders in the area, such as the new Riverlight residents, 9 Elms houseboats, the Battersea Power Station development, and Corrie Environmental, many of whom are already familiar with the JV, having recently been appointed principal contractor on London Underground's Northern Line extension, of which the main site lies just south of the Kirtland Street worksite. As principal contractor, they will be able to seamlessly coordinate site logistics and both vehicle and marine movements. This advantage also applies to the maritime consents required with working within the river foreshore, something that the JV have a lot of experience with, having extensively used the river as a delivery route during the construction of the London 2012 Olympics, and now the Northern Line extension. On site possession, the initial mobilization will commence with the erection of the hoardings and the laying of a concrete hardstanding to enable the site accommodation and welfare offices to be constructed. The major piling works for the loading jetties, gantry cranes, camp shed and foundations comprising of both marine and land-based units will start concurrently. Sheet piling will be installed to enable the safe excavation of the drop shaft down to first formation level, after which the construction methodology will change to sprayed concrete lining. The construction of a travelling hopper or conveyor system for spoil removal and a gantry crane for material deliveries will be assisted by the erection of a 50-metre rail-mounted luffing jib tower crane for general site distribution and construction duties. During the construction of the shaft and launch chambers, a pair of Epb TBMs will be delivered by barge and assembled on site in readiness for pre-testing and commissioning. After which, they will be lowered down the shaft to commence their drive east towards Chambers Wharf and west towards Carnworth. During the main tunnelling stage of the works, a full-height enclosure will be built to minimise noise and dust pollution to the local community. The first TBM will drive westwards towards Carnworth Road, followed by the second TBM starting its drive eastwards towards Chambers Wharf. An elevated conveyor, including a vertical section, will be used to bring the spoil from the TBM up to the spoil heap at ground level in the southern compound, prior to depositing it by travelling hopper or conveyor system onto the awaiting barges. With the TBM tunnelling operation in full swing, the site layout and associated marine movements continue with a routine of spoil removal and segment delivery and storage. In readiness for the construction of the concrete secondary lining, a batching plant and conveyor to the existing Cemex jetty will be built. The shorter western section of the tunnel will be completed first, and the TBM parked just short of the receiving chamber at Carnworth Road. With the primary lining of this section of the tunnel completed, the secondary lining works can begin. Commencing at the rear of the TBM backup, the secondary lining will be installed working back towards Kirtland Street. Rebar cages for the secondary lining and tunnel segments will be delivered by barge and stored in the yard for subsequent delivery to the tunnel via the gantry crane and drop shaft. Upon completion of the longer eastern drive of the TBM to Chambers Wharf, the site will revert to servicing predominantly the secondary lining works. With all the secondary lining works completed, the last major works will be the construction of the ventilation shaft. During this period, the noise enclosure will be dismantled and the site made ready for decommissioning. And finally, site hoardings erected around the northern and southern compounds for future development. The JV will work with the Prince's Trust, local authorities, schools and colleges to bring new skills and employment opportunities across the lifetime of the project and long-term career opportunities for the local community. The Ferrovial Langer-Rourke joint venture are committed to working collaboratively with Thames Tideway Tunnel and all Alliance participants on the adjoining contracts to create a cleaner, healthier River Thames and to make a real difference to London's livelihood. A legacy for future generations.
Okay, sorry, can I just say, you heard that audio okay on that video, yes?
Yes.
Good.
Yes, sir.
Okay, just a couple of shots now show some of the when we went to do the factory acceptance tests in France. This is always great in EPBs if you can get it. We've got the decompression chambers here, and then an anti-chamber before you can go into the cutter head. It's always good if these can be designed in, particularly when you could be working in very high compressed air. And so we ensured there were this kind of large anti-chamber before you got inside the cutter head. Just some general pictures. Okay, the project scope, the TBM delivery, lifting transport, TBM components from the jetty. So what we'll look at now basically is how we delivered the TBMs. They had to be driven from Le Creusot in southern France, which is near Lyon, drive up to Zeebrugge port in on the outskirts of kind of Germany, going into Belgium and Brussels, and then there they got these ships, which then brought them across the English Channel and around the Thames. The Thames leads into the sea, and they were brought up into a long way Thames into West London. The trouble we have with that is the large ships, vessels, what had to come in to bring this equipment in. We had to bring them in during let me get this right, during a neap tide. If I think I've got it the right way now. So we could only come in in any month period. We had a 1 week window in every month approximately to bring TBM components in, depended what was happening. And it can only happen during a neap tide. I think I've got it the right way around. But basically what it means is it's the barges could only come down the Thames when the tide was flowing out, when it's on a low tide. And that is because a ship coming up, you need to park. You can't park it up with the tide running away from it, if that makes sense. So the TBM is, say, the ship is coming, say, from the east, and you need the water running west. Yeah. You need the water running east and the ship moving from the east towards the west so it doesn't float away with the tide. So it kind of, with the barges, can help stop the movement of the ships. But what we had to do was also, that wasn't just the constraint on what the tides were doing. It was also, the other constraint was that it had to be the highest, lowest tide. So obviously you get high tides and low tides, and you'll see in some of these videos the tide ranges we have, and we can get up to 6 meters tidal ranges because obviously we're very north. So what we had to do to make sure the ships could get under the bridges, we had to bring them in at the highest, lowest tide. The very low tides were no good because directly after the highest low tides, you get the lowest low tides, and you had to get the empty ship back out. So it could end up, if you had any problems unloading those components, that you couldn't get the boat back out, and you got massive fees where these boats would have to wait 2 or 3 weeks before they could get out on the Thames. And that wasn't without problems of, if there were lots of rainfall, for a sustained period of rainfall could result in that the Thames Barrier, there's a barrier in London, to the east of London, Thames Barrier. If you don't know what it is, have a look at that amazing feat of engineering, where they can hold the water. Actually, what it's for, it's to stop water, the tidal range, is to manage the water levels, basically, and stop flooding in West London. So, excuse me, we'll have, so there was lots of complexities with delivery and the type of ships and how we could unload it. So what we had to do was build a jetty out into the Thames where we could put a crane out and to pick up these units. So these are the component weights. It's just part of the presentation. But and we had loads. I think the heaviest load, we got one here. Look, if we look at this, 160 tons. So some of the, so I do apologize, 110 tons. I think was it gantries? The gantries are solidly built. They were when they were erected. But offloading ships, I do remember, is about 110 tons. So location of works in plan view, Kirtland Street, right next to the Thames here. This is the river. This blue line here was basically we were not allowed to encroach to the side of that. So when we spoke, there are two companies, actually, and there was only one company. The two companies to unload this type of equipment, one was called ALE, I think Abnormal Lifting Engineering, and the other company is called Mammoet. This company, huge worldwide companies, and maybe I'm sure some of you have heard them. They can pick up, they're just amazing for dismantling and not manufacturing, but heavy lift companies. They have ships with cranes on them, things like that. Mammoet has just bought ALE, so now ALE doesn't exist. So this is what we had to do. We had to bring boats to here, and this is an existing dock here, and we had to build our own dock on this side to unload the boats. So we'll have a look at the how we did that. So what we did is we had to build this special sheer leg crane with strand jacks to unload the ship. So this is a ship, this is a jetty we built, and then what we did is we could then bring these SPMTs, this here, up through this sheer leg, which you'll see a bit better. And for this one, I'm just trying to think, we would bolt two of these together, because these units, these wheels can turn 180 degrees. They can almost do they can turn on their own radius. Yeah, they can almost turn on their own radius. And we used to bolt two of these together. When we picked up, what we did is we brought the component parts by ships, built the TBMs up on the surface, then transported them, lowered them underground, which you'll see that shortly. And we did that by bolting 4 of these together later. You can actually connect these together, and by one controller they all work. So this is how this is kind of the equipment we use. You've got these special gantries, these special jacking, sliding, so they can move, and these are the these strand jacks. So it's kind of, there's always load on, and it's for heavy lift type equipment. So this is the setup. This is us building up the this is the strand jack, the system. So that's how we built up, so we could get the SPMTs underneath here, put the SPMTs in to actually move this onto the jetty. So we could move it onto the jetty and await for shipments. Then we could unload the boats and put them on the SPMTs, move them back. this is an actual picture of one piece, and I was wrong actually. It was only single we did. I do apologise, my mistake. I thought it was two we bolted side by side. So then we moved them to, there's an actual picture of happening with a crane. What we did is we had this strand jack. I'm sorry it's bad image. I couldn't find a good image of it, but here it is. We only actually used it for one shipment, and then what we did right at the very last minute, I was able to change what was on this shipment to the point where then we had something like 10 days before another ship came in. And to be honest, this thing was very, very slow. So I had 10 days to remove this, dismantle it, take out, there's like a runway it ran on, like a railway type thing it ran on, and then bring in the big heavy crane, which we already had there, because this was faster, and we just managed, I think the weight, from memory, the weights were 5 ton less, so it allowed us to use this crane because we had a problem with the loading of the, well, I say a problem, we had a weight limit on the jetty we built, so we changed it. So we only used it for one load, and we managed to put all the heavy pieces on one shipment and then get rid of it. So we put the 2 bearing pieces in here. Those were the kind of the heaviest loads. Okay, so we then unloaded the pieces in our laydown area. We built up the gantries, and this is the 2 TBMs parked up, built. Now this distance from here to here is approximately 3 meters. Now, when you consider you've got a TBM nearly 9 meters, that's 12 meters in the air. Now, that is, scale of it's massive. And the reason we did this was because these cradles here were also a lifting beam to lower it down the shaft. So they weren't just to build it, they had obviously other loads, so that's why it's quite thick, heavy steelwork. And then we need to bring in these SPMTs to pick these up and move them into the shaft. And that's why you see we've got that. Then these are just columns, dismantle. So we could pick them up and then move them into the shaft. You can see, so this keeps jumping by itself. There's an actual position. And we actually bolted 4 of these together. So you've got 1, 2, and then 2 all the other side. There's 4 of these. And you can see there that kind of angle of how, it's almost turning there. 0 radius, if that's correct. From here, it's just literally turning on itself. It's amazing equipment, and I don't know if any of you've seen these or used them, but we use them a lot in heavy lift TBMs. So what we did then is we took them into the gantry, and we then built inside our acoustic barrier. The shed we use a massive big acoustic barrier, and then we would we built it, and it's built at high level. Bring the TBM in, then lower the heavy lift gantry, move it over the shaft like that. This is the actual picture, of course, and then we could lower it down to the bottom of the shaft. It took about 7 hours to lower down, and then what we did is we put SPMTs then underground, and the reason for that is the crane, this heavy lift gantry we used, it couldn't turn the TBM, it just lowered it in one position. So what we had to do is, it's not like a normal crane where you can turn it on the hook turns type of thing. With this kind of equipment, it doesn't turn, so you've got to put something else down there to align it with the two drives. We'd actually built 2 tunnels 37 meters long, which the TBMs were then going to go inside of these 2 tunnels. The 37 meters long, I was under a lot of pressure only to make them 25 meters, but in the end I managed to get approval to make them 37 meters long, because what we could demonstrate was that by making them longer, we saved time, because we were able to build the minimum number of gantries were all what needed to be there, because otherwise what it would have meant is that one gantry would have to have gone down into the shaft to power the umbilicals to a part of it, and it would have been in the way. So to make that TBM 25 to 37, by making it another 12 meters longer, meant it saved time on reinstalling another gantry later, and it speeded up commissioning and the initial drive. So we could save nearly a week doing that. Although to dig, you could imagine that this 9, I think it was getting on for nearly 10 meter. This NATM, well, not NATM, it was an SCL tunnel. Got to be careful there on my terminologies on design. It was an SCL, 2 SCL tunnels were built. So it put more time on the program, but overall we could demonstrate it was less because of the TBM commissioning. So we dropped the TBMs down onto these SPMTs. We could align them then with the tunnels. As you can see, there's aligning it now with the tunnels. Push them in, so we could use the lifting gantry. Then was part of the system. We could jack the TBMs forward into the caverns, into the chambers, and then we built in this SCL cavern. We had quite a large thickening there, and we had to be very accurate on alignment, and then quite a large thickening where we then bolted on a shove frame and a ceiling and a special double seal, same as one we're using in Bangalore. So we could inflate the seal around the shield. So when the TBM launched, that you had a seal around the steel can. And then as the TBM then moved off the seal, then there was a secondary balloon on it, secondary layer, where you could inflate it again, and it would inflate along the segment. What you can do, it's kind of normal practice where you can do that in these caverns, so you stop against any kind of we could have had something like 3-bar pressure. There was some depressurization taking place, and we had depressurization wells, but there was a big issue there on potential high water inflows. Sometimes what you can do as well, we didn't need to do it on here, is then you can, once the TBM had gone in 1 meter, sometimes what we do then is we'll inject around the TBM. I'm going to use the word clay shock material. And if you don't know what clay shock is, please have a look at TAC website. TAC is a company who supply our A and B component instrumentation and pipe work, what we fit inside of the tailskins for the tailskin grouting. But clay shock is a mixture of bentonite, cement, and sodium silicate. So you can inject around TBMs, and it's good for launches like this, where you want to seal against groundwater coming in, and you put this soft clay around the TBM so it doesn't stick the TBM up. Can I tell you, it's like a lot of products nowadays. Years ago, that kind of product we used to make ourselves, and it's something I've used. I remember you being shown something like that in the 1980s out in Egypt, when you get lots of particularly with TBMs, and you get particularly mixed phase conditions where you get big holes in front of the TBM and you can't enter the TBM because the compressed air is leaking. You might have a big void in front of you, and what we do is I'm going to use the word clay shock again. We would inject the TBM head, the slurry machine. This is what we're doing in Bangalore. This is what we're doing in Bangalore quite a lot, by the way. Not with clay shock, but with my own clay shock. And it's just bentonite and cement and sodium silicate. And what you do is you can fill the cutter head up with this material. You're injecting it outside as well. You fill the void up outside as well. And then after 24 hours, you go in. You can open up the cutter head, and you've got this thick clay you can dig out. It's a bit laborious, but at least you can get head entry, and you fill the head up. You can get in. The compressed air will then hold, and you can then change the cutters. It's something we used a lot on Bangalore Metro Phase 1, and it's something we'll be working with the crews, the L&T people in Bangalore Phase 2, and we'll be giving them the mix design to this kind of material. Something we use a lot of. It's for breaking out TBMs, breaking in TBMs. So if you don't know about clay shop, have a look at the TAC website and they'll tell you about it. And it looks like A and B component tail skin grout, what's gone off, although it's browner, and it's gone off within a short period of time, very thick. Okay, that's the launch shield. I just want to show this TBM mooring video now.
We've had some good completed work, so we've actually finished our River Wall 922 strengthening works, which is right down the other side of our site over here. We're now in the process of handing back to London Borough of Hammersmith and Fulham for them to complete the reinstatement of that footpath and to give this back to the public. Further to that, we've done some more River Wall work, which involved installing merino oak fenders for barge protection. These will be things that we left in place for the safety of the public when they're yachting or rowing along the River Thames themselves. We've had to install maybe 9 or 10 pressure relief wells that we can go and pump, lower the water level down, which allows us to carry on shaft excavating without causing a safety issue.
We've prepared this site, the TBM's arriving, now they've been reassembled and they're ready to go down the shaft behind me. We put them on these movable units known as SPMTs and brought them from their location by the office into the shed behind me.
The plan is to take her into the shed, do our test lift, get her all ready.
We will lift the gantry up over the TBM, lower it back down, connect it up, test lift, skid it out into the shaft.
Given that it's a 1,000-ton lift, it needs some heavy-duty lifting equipment. The machine we're using is called a strand jack, and it's essentially clamped in 4 locations, so you've got that extra measure of security and safety.
From there, over about 8 hours or so, it's going to be lowered very, very slowly to the bottom of that 53-metre deep shaft, and then jacked into position into the tunnel adit.
The Eagle has landed. We know that we're really getting serious now about the start of the tunnelling operations. There's almost 25 kilometres of tunnel to be built. Just to be here to see the start of that today is really exciting.
We can start our main bulk excavation for our shaft. We have a team of archaeologists on site excavating down for 6 metres.
We in 2015 already excavated some archaeological trenches, and back then we found a series of river walls or revetments.
Well, these are 3 of the finds today from the 17th century docks. They've just come out. One's a William III penny, 17th century buckle and some kind of ring.
Done really well so far.
If you don't get that thing down that shaft, it's not going to be able to do its job.
It's really exciting.
Was it easy?
If it looked easy, then we've achieved our aim.
Okay, just again, we're coming near to the end of the presentation. You heard the audio to that video as well, yes?
Yes, sir.
Okay, good. What I want to show you now really is just the conveyor setup, just a few setup, what we did. This is the shaft here. We've got vertical conveyors coming up onto a cross conveyor. So what we could do, the way the soil came up, it came up here, then it went to this storage area here, and this was a busy Kirtland Street here, so we had above ground conveyors, above this. That's the reason they're above here is because they have to cross a busy road. And then we had a buffer area here. And what could happen is just here, if we didn't need to put the soil here, for example, there could be a problem with the
Russell, the audio is off again. Thank you, Sandeep. Whoever has joined in last 30 minutes or so, if you have any questions, you can post them in the chat box of this webinar, and we will take them to Russell in the end.
Okay, I'm back again. You can hear me okay?
Yes. Yes, sir.
Okay, listen, I'll just reload up. I'm nearly finished. Not much more to go. Just I'll give me 20 seconds while I just reload the presentation. Second. Okay, can I just ask a question? You can see the video online? Yeah?
Yeah.
Okay, good. So, vertical conveyors here coming out the acoustic container shed, ran to a buffer stock area where we actually, part of the contract, we had to design a system, and the reason it was quite elaborate in doing all this is we had to have a system in place where we could do 3 days of excavation without relying on the river in case there was a problem by river, which can happen on the Thames because of particularly high intensity rainfall. If the Thames Barrier has been closed, you can actually stop tunneling. So that's kind of the outline. A radial stacker here, by the way, there is radial stacker there and a radial stacker here. This one was fixed in the height. This one could go up and down because the River Thames goes up and down 6 meters. So this radial stacker here had to literally had to run up and down by 6 meters. The reason is you can't drop it from a very height because it's kind of wet material. It splatters and you can cause environmental issues with deposits kind of going everywhere and going into the River Thames itself, which is an environmental issue. So just another view of it in plan view there. This is a closer view. 2 vertical. Each TBM had its own vertical conveyor. This is the installation of this. What the vertical conveyors look like. what you do is we combine, when we build these vertical conveyors, we specifically ensured we had a walkway around all these, and that's so you can do maintenance, we can change rollers, we can do all kind of maintenance. And we also had a walkway down the centre of them, so because of the the regulations on two means of access and egress, so we designed in maintenance and general emergency access and egress into the tunnel and out of the tunnel. So that's what you're looking at. That kind of kills two birds with one stone. The main access for up and down was we had two crane gantries in here and access there. Sorry, the main access you can't see. I do apologize. I knew something else. The main access was an Alimac conveyor. 2 levels, so we could carry something like 25 people in one ferried up and down. Shaft was approximately 60 meters, and you'll see in a minute why we had to design it in 2 levels. So you've got one level where all the rolling stock comes in and picks up the segments and rails and pipes and things like that, and then we had to have another layer below that for the conveyors, for the soil to come out of the tunnels, drop down a chute below the where the locomotives are, drop onto a conveyor, come across, and then go through a sizer. And what we do is we want to make sure there's no big clay lumps when we're using these vertical conveyors. So it goes through a sizer, like what we use on Surrey machines. Sometimes we would use rotary crushers on Surrey machines. They're basically rotary crushers, and the material, soft clay, goes through, breaks up any lumps, and when you've got these vertical conveyors, you can't have any problems with outsized lumps, because it would cause the 2 belts not to close. You'll see how they work in a second, and we treat the soil coming up basically. I'm just going to quickly show you a very good video on. Now this video was made for the Northern Line extension, but we used a lot of the material from this project. So when it looks at the conveyors in the tunnel and the vertical conveyors and the stacker onto barges, all this happened within a few hundred meters of our tunnel, and we used a lot of the equipment after. So it's only about 9-minute long video. I won't show all of it. I just want to show you the relevant bits, so I'll speed it along in areas.
Derived from an enormous reservoir of experience and know-how. Building on the history.
Sorry, and can you hear that audio with it, by the way? I can't remember if I pressed the button to it on this one. Okay, you can hear the audio to the presentation.
Of our legacy brands, Continental Conveyor and Stamler, engineering heritage and adherence to high-quality out-of-sight service logistics. High-angle. Our materials handling equipment can be incorporated to support either traditional TBM or drill and blast applications. Tunnel conveyors can be supported either from the tunnel roof or on wall-mounted brackets. Unlike the use of rail-mounted muck carts, there's no disruption to tunnelling work. As the TBM drives further into the excavation route, new conveyor structure is added from the safe confines of the backup area. Once tunnel conveyors emerge from the ground, they become part of a surface scheme configured to deliver the spoil for additional handling. This can be by transfer to storage for direct spreading, or onward movement by truck or water transportation. The surface arrangement can be very complex and relatively confined, so the need to avoid obstructions is commonplace. Tunnel spoil can be elevated to surface level using a flight of conveyors or via the high-angle conveyor. During this process, the material may also need to be sized. This can be undertaken by our range of material feeders and crushers. As tunnel segments are made ready for transportation to the tunnel boring machine, the wall-mounted conveyor reliably removes spoil without interfering with tunnel traffic. On curved stretches, the conveyor safely contains the spoil as it moves along. As tunnelling progresses, the supporting framework for extending the conveyor is constructed in the backup area of the TBM. The belt storage system is an important aspect of the project and enables the tunnel boring machine to advance without interruption. As the storage system empties, the carriage moves forward. New belt is added by cutting the existing loop and inserting and vulcanizing a new piece in situ. The carriage is then pulled back into its start position by a hydraulic or electric winch, and as a result, the storage magazine is fully replenished. On completion, the belt storage loop is reconnected, creating a complete loop. As the TBM moves forward, the spoil passes through the backup area transfer point. It's then transferred into the our complete electrical variable or compass system control logic. If the point of delivery from the tunnel is deep below ground, then it can be carried to the surface using a high-angle conveyor. High-angle conveyors were pioneered by Joy Global to provide an economical and reliable way of elevating spoil vertically or at steep angles of inclination away from the area of excavation. The high-angle conveyor sandwich belt concept involves a fully equalized pressing mechanism which secures the material to the center of the belt while effectively sealing the edges of the two belts together. It holds the material continuously, removing relative movement between the material and the belt. Another factor is that it uses standard belt cleaning components for greater economy when handling wet or sticky material. All of these features mean that high-angle conveyors provide greater efficiency and greater operational control compared with other methods of elevation. They have the advantage of reducing in-shaft traffic, reducing craneage requirements, and reducing downtime, all resulting in lower operational costs and maximizing efficiency. In inner-city locations where space is limited for handling.
Okay, so that's basically how a vertical conveyor works. I'll just kind of conclude very quickly. So we had the vertical conveyors. This is showing the radial stacker onto the barges. This is the radial stacker at the end. Just wanted to quickly show you this, so how we actually do it, the lay at the pit bottom. At this level here, where this brown level line is here, this is a railway line we fitted, and underneath there obviously was a decking. So what happened was the soil came out of the conveyor, would drop down here. Sorry, what you've got here, I do apologise. What you've got first of all is, when you saw on that picture earlier, you saw a horizontal belt loop where we normally put 500 metres of belt in to give us 250 metres of tunnelling before we need to change conveyor belt. We don't really like fitting horizontal belt loops inside of tunnels, because when you've launched the TBMs, you then have got a delay in installing them. So what we do is, you'll see in here, we installed vertical loops. So it gives you the added problem of how you set shafts up. So what we had is, I'll show you one, and then you'll understand how the two works. So the conveyor belt came here, ran down, ran across. You can see it in purple, and then went up here. So in here you've got about 7 or 8 loops. So when we're tunneling, the loops come together, and that's how we do 250 meters of tunnel by a vertical storage unit. There's one there, and there's one here directly opposite the other tunnel here. The soil had to come out, therefore, by coming to the end of the belt, dropping down here, and in here there was what we call a sizer, what makes sure there's no lumps in it. Then along another conveyor belt, dropped it here. Excuse me. What happens is the soil then comes along here, and there's these two belts. There's actually 2 conveyor belts here, and the soil comes between the 2 conveyor belts. And as you saw in the animation, it traps it together as a sandwich and runs it vertical. So we actually had quite a busy site here, and it's quite a difficult and very, very interesting area where we planned and designed this with several manufacturers and ourselves, sat in many meetings to get it concluded. You can see a very good view there where the soil comes out, drops down here. This is a sizer, drops down here, comes here, and then you see the 2 belts here. You've got the top belt and the bottom belt. Comes here, then runs up, and it's sandwiched through this lens here. And then this purple belt here is the actual storage belt for continuous tunneling. Just another view of that. You can see the complexity. Very quickly, the launch jet sequence, literally 2 or 3 minutes to go now. So what we did is, this is the 37 meters added, where we could actually put this gantry. It was very important to get this gantry. Many reasons. It was a last gantry for, this was the main gantry where the soil came out of the screw and came over an angle and came to here. So, and that would feed onto the main belt to the end of the project. So it was good to get this conveyor in. Otherwise, we'd have to move to this location back to here. It would have meant lots of modification to this gantry. That was the initial plan. I particularly thought it was well, when we did it on the program, it didn't really stand up, where we could look at that, install this here, or otherwise it meant this gantry literally had to be down here and be part of the umbilicals to this, so it didn't stack up. And so we were able to do, by extending the TBM by 12 meters, we're able to put this minimum number of gantries on so we could quickly do launching. This is a temporary conveyor here we installed, so the TBM could run from here. It could run all the way to here before we had to put all the gantries in. You can see how it went forward, adding gantries. We went along to the point then where we'd got the last one in. Then we could then launch the second TBM, and we could put radius track in here so we could keep tunneling on this drive whilst we were installing the second TBM. And basically I'm doing that very quickly because we've come to the end. I hope I didn't rush the last bit too much, but thank you for listening. I took a bit longer than I thought, actually. So that's the end of the presentation, and thank you for listening. Thank you very much. If there's any questions, please, I'll welcome anything you'd like to ask.
Thank you very much, Russell. And few questions are there in the chat box. If you could,
I presented to you.
Yeah, I'll just come out the presentation and have a look at the chat box then. Just 1 second. If I start at the beginning, let's have a look. Okay, let's have a look. I'm looking. How settlement and damage to nearby structures. Yeah. Sorry. I'll just read it. How settlement damage to nearby structures managed during the construction of shaft along the TBM, as there were several high-value assets around. when we did the shaft sinking, it was very, very stiff clay, and the nearest structure you saw, the brand new apartments, they were actually down on piles, very deep piles, and the closest, the shaft was something like 60, 70 meters away. The biggest problem we had there was adjacent to us, there was an old jetty where there were lots of houseboats, and the biggest problem we had was environmental in respect to noise, to be honest, and we have to get very stringent requirements on planning application for environmental considerations, noise, lighting, dust levels, vibration levels, and we just worked within everything, and we had no problem with settlement. The ground is very stiff clay, and you get very little settlement. It wasn't an issue at all. Just running down, can we say that clay shock has a similar purpose action as that of bull flex O-ring? Well, a bull flex ring is no, it isn't the same thing. A bull flex ring is what I was talking about. We've used them for many years, and we make, in fact, when you say O-ring, you can make any shape you want with the bull flex O's. In fact, I've used them. What I've used them for is in sheet piling excavations. When you put a frame in, for example, when you put a frame in a sheet piled excavation, you've got this not undulating, W section sheet piling, and you want to fill them gaps up. You can get square bags of bull flex O's, fill them up with grout, and you can support all kind of shapes. For the O-ring shape, what you're talking about, we use them in shaft sinking. We would excavate 2 underpin rings, put a bull flex hose around it, expand it so we can grout the rings up in vertical shafts. And we use them for obviously tunneling. I've certainly used them for putting around TBMs when we're going to break into a tunnel. The one you saw, we fitted it inside of I nearly said NATM, SCL, an SCL cavern, where we, as I said, we put it around the steel TBM, and then as the TBM went off it, it had the secondary hosing on it where we could then expand it onto the segments. That is just a seal, and that seal worked, probably about, the bull flex hose sealed on the rings by about 600 millimeters. It's circular, but it's obvious it goes rectangular because it doesn't blow up to circle. You need that bearing area, and it was designed to withstand, to be honest, about 5 bar, working bar pressure of 3.5 bar. The clay shock is something different. The clay shock it's a material we would use, and have a look at the TAIym website, you'll see pictures of it. But can I tell you, it's something professional tunneling managers know about, and we make it ourselves. If you buy the clay shock from TAIym, you've got to get special. You've got to buy the products off them from Japan or whatever. You've got to get special mixing facilities. If you've got a slurry tunnel boring machine, you've got everything you need. You've got a slurry treatment plant, so you can mix up large volume of slurry. And you've got grout tanks underground. So what you do is you can add the slurry to the grout tanks underground, mix the slurry and the grout together to a viscosity of probably about 50 seconds, and you add your sodium silicate to it, so it goes off like a toothpaste consistency. So what you're doing is that will provide a what's the word I'm thinking of? That will provide a seal. So, for example, we saw that TBM we had in London, probably about 12 meters long. You've got your O-ring seal. You've got to bury the TBM head in by about 1 meter so you don't fill the cutter head up. But can I tell you, there's not a problem. You can fill the cutter head up with it as well if you want to. If you thought you were going to hit pressure immediately, then you can fill the cutter head up with it. It isn't a problem. So when you mine out, you've instantly got a plug of material, which is it's soft clay. It's malleable. That's not the right word, is it? It's soft clay. You make it as soft and as stiff as you want. The longer you leave it, of course, it'll dry up and go very hard. But can I tell you how that was developed? Now that's for helping to launch TBMs. That was developed, I used this in the late 80s in Egypt. We had sudden machines there, and we had, what we used to find is when we were breaking out of shafts or breaking into shafts, we were going through very high alkaline ground because we were going through tuber-manchette, ground-treated areas, and we would lose ground. And so we'd have voids in front of us. So we had big problems. So we'd fill the cutter head up with this soft material and the void outside, and that meant you could get in and put compressed air on and get inside the cutter head. Now, can I tell you, I used this and introduced it to our tunnelling team in Phase 1 Bangalore. We had to do this about 15, 20 times in Bangalore Phase 1 just to get inside the cutter head. If you don't, can I say, this material and mixed phase tunnelling go hand in hand together. If you buy a TBM, you attempt to take on a tunnel boring machine, so it's EPB or slurry, and where it comes in very useful, by the way, if you've got an EPB and you've got undulating rock, you do a head entry. Your EPB, this is why you pick slurry machines in Bangalore. Obviously for you with an EPB, you have to drive forward about 1.5 meters before you've got a plug of concrete. If you've got 200 MPa rock in the bottom of an EPB in somewhere like Bangalore, how are you going to? Your only phase protection is using compressed air, which you can lose very quickly. So that's why you could pump the head full of this clay shot. You've got a plug of material. You can do your pressurized tunneling and move forward. But it's mainly in Bangalore for mixed phase tunneling causes voids above you. and it's impossible in mixed phase. You look at everywhere around the world, Singapore, very high strength rock in the bottom, soft ground above you, you over excavate, it cannot help it, because you're going inside these cutter heads sometimes every 2 or 3 meters. So we mix this material, pump it in front of us, fill the void up, compressed air will hold, you can go in, and it's simple to use. So I think the bull flex hose is just a seal around a TBM or a ring, and that will withstand pressure. But the clay shot, just to finish the answer there, it's got a lot more uses. But I think I understand what you mean about it provides a seal, if that's what your question was. Yeah, the opening aspect ratio for 2 TBMs having 20% difference. Yeah, what it was felt was the design of the TBMs, which is pretty standard, by the way, and I certainly add it into L&T's procedures. EPB tunnel boring machines. We normally say we want them designed, and the backup, we design it on 100 millimeters per minute excavation rate. So all them conveyors you saw and the number of barges and everything what was there was designed around 100 millimeters per minute advance rate. Now, you need to design something like that to realistically manage something what might be doing 60, 70, 80 millimeters per minute. I've seen TBMs in Delhi in that soft alluvium do 90 millimeters per minute. It wasn't sustained because you couldn't get the soil away. But some of the, there's been some record broken in Delhi with some machines. Over a sustained period of time is difficult because, sometimes you can't get the soil away, you can't work nights, you don't have the area. In London, we just so happened to have a little bit more area, and we could sustain that type of progress of about 60, 70 millimeters per minute. Now that's fantastic tunneling when you're doing that very easily. So everything's designed on 100 millimeters. So the cutter heads are designed for rate of advance and speed, and it was predominantly clay on the west drive. So to have the higher higher opening aspect ratio was to get the soil in. Otherwise, it was the other way around. It's a small, bigger opening for the more clay, and that was to just for speed and design of the cutter head. To be perfectly honest, for speed of tunnelling. So the west drive had 50% and the east drive had 42%, and that was again just for speed because it was thicker clay. It was thicker and stiffer clay. When I say thicker clay, it was stiffer clay. I do apologise, and it was to help reduce the torque of the TBM. So it was all kind of allowed for, designed to keep the torque down and to get the material in. Where on the east drive, the 8%. When you consider a hard rock machine only has 5% opening, the 8% is a lot more, and the east drive was 42%, and that was predominantly because it was going through a mixture of sand and clay, but that made it faster tunnelling because you got the coarse sand mixing with clay, so it allowed it easier to get through the soil, basically. I think, does that answer? I think why EPB TBM has been chosen in soft ground condition projects? Why not Surrey? It was predominantly clay, and Surrey machines the Surrey wouldn't have worked. It would have just been you would have mined. There was too much clay there, and even if you'd used like a polymer or very low viscosity, the drilling mud would just turn into a very thick clay where you'd have to be going very, very slow. EPBs and clay go very fast. Surrey machines and sand go very fast. So they both not the same. I hope that answers your question. What's the difference in the muck removed out of the tunnel in both the conveyor systems open and closed? When you mean pressurized mode or pressurized or not pressurized mode, if I think that's what your question is, there shouldn't be any difference. It's got nothing to do with the conveyors. It's what you've got to do is whichever, if it's open or closed mode you're working in, you have to ensure that soil is not too wet. Because if it's, for example, with an EPB, if the soil's too dry, we've got to add polymer and water to allow us to drill through it faster. So we have to condition it, and then we've got a problem then. If we make it too wet, then it won't go up the vertical conveyor. So we have to be very careful with the type of additives we use and how we condition it. And it makes, with vertical conveyors, by the way, gives you another huge, I'm going to say, headache of managing tunnel boring machines. It's hard enough without having a vertical conveyor belt, but if you get it right, which is, that you've got to put the effort in and do a lot of the planning. And in fact, when I went to Tideway, I made the conveyor belts wider. I had to spend another $100,000 US, but I made them wider, and it allowed us to put wetter material and then go faster. And to be honest, and I changed the I changed the sizer, this MMD sizer. Have a look at that company online, MMD sizers. It's the rotary crushers, and we use them in soft ground. And I changed that, made it bigger, and we could, and it's proven what the changes we made has made amazing progress. What they've done there is very, very, a lot of fine detail. It was a particular job. Look at the fine detail, and the tunneling would have been, I'm going to say easy. It's not. I'm sure if anybody's listening from Tideway, they'll hate me for saying that. Okay. Was there any additive to make the spoil cohesive? Yes, of course. What we had to do was we looked at foam. That's what we use in clay. We looked at foam, and we had to look at that quite early on. And we looked at about three or four different companies and suppliers, And we had to look at it very early on, and we had to get the environmental department's approval for it, which took about 3 or 4 months because we had to give them some of our, not give them, but give, we had to give to a consultant some of the soil, some of the foam, and then they had to look at it, do laboratory tests on to see bacterial build-up and see if it was detrimental to the environment. So we had to be, it's not like maybe a lot of other places where you just change the foam. Sorry, the question is, I don't know if you understand, by the way, that we had foam, which is a mixture of detergent and polymer to condition the soil. And when we talk about tack, by the way, and this clay shock, and this is why I find it interesting. Many years ago, nobody made foam. Nobody made it. But as a young engineer on one job I had, God, I can't remember which one it was. My boss said, by the way, you've got to make some foam. And I said, what's foam for? And he said, well, we inject it into these Epb machines and it conditions the clay material and stops it being sticky. So I said, well, how's it made? He said, well, it's polymer and detergent. And he gave me kind of a very, very very crude description. Then I went out and then investigated this, did some research, got polymer, got foam, knew about air, what you call it, air infusing of it, developed some equipment, Grotin mixing pans and injectors, and knew by adding air to it, I could make a foam. And by adding different amounts of polymer and detergent, we got different results from it. So again, years ago, it's like tunnel guidance systems. Years ago, the tunnel guidance system was an engineer and calculator, and a laser, and you had to tell the TBM what angle you were going and the offsets, and that. So it's quite interesting being an older engineer now, and the conventional work to now, and it's really interesting for me to see these developments and how although what I can say is when tunnel guidance systems break down nowadays, or you get a problem with the segments, then people are looking at the computer to wonder what they do next. So some of the skills I think are still needed when you get some of the problems. Whether there's any problems, we had no, not really, no, because we had very good universal segments with dowels, casting, gaskets. We had a good product, and nothing was a problem. How do you calculate the pressure that is to be applied in the EPB shield? Well, what we do is we know the pressure of the soil by the GSI, the geotechnical site investigation. So we know what the hydrostatic or overburden pressure is. And what we do is when we are mining forward, if let's just say I'm going to put it into understandable numbers, if I may, for 1 minute, and pardon if I'm sounding whatever. Let's say we're 20 meters underground, and that's 2 bar pressure, which is 30 psi approximately. When we're mining forward, we would mine at 0.2 bar higher. So if we calculate or can see 2 bar pressure on the TBM, what we would do is, let's say that's 2 bar, just for a number, we would mine 0.2 bar above that. And that is so we can balance with an EPB, which is the high percentage of clay in the cutter head, or using a drilling mud, which has thixotropic properties and will not dissipate into the surrounding ground. We will use either the soil or the drilling mud, or the compressed air, by the way, 0.2 bar above the hydrostatic or the overburden pressure. What that does is that stops water and ground from falling into the cutter head uncontrolled, because that is over excavation. and normal designs are normally 0.4% on design for settlement troughs. In Tideway in London, we had to protect all the above ground structures, river walls, anything with a zone of influence, to 1%, which is quite, I'd never seen that before. So we had to ensure everything was protected to 1%. Of course, we'd be tunnelling in them conditions probably about, you know, I think we couldn't do it on a design point of view, but we would have been about 0.25%. It would have been almost negligible. And so it's, we know the pressure, we know the diameter of the TBM, and we know what pressure is going to enact on that TBM. And can I tell you, the thrust of TBMs is far above what any face pressure, you know, it's all designed, the TBM is designed to overcome the thrust pressure, and that's part of the design. Nowadays in Europe, we do category 3 design check, and and that a lot of the design, a lot of TBM companies don't like that, because it's the true sense of category 3 design checkers that say Head and Connect, for example, they have to give us a design for the TBM which an independent person has designed. All they are allowed to give that design checker, they're not allowed to give them the drawings and the they can give them the drawings but not the calculations. So it's not a design check on calculations, because that's category 2. Category 3, if you look at the wording of the specification, is an independent company. All they do is they'll say, well, you know, what are the loads imposed? What's the kind of general criteria? You're drawing, you know, you've got, say, 50 mil steel plate with gussets whatever, and they will do their own design and say, yeah, what you're doing is correct. So a lot of it, we check my proper category 3 to check. That was a stipulation in Tideway as well. There was a double line tunnel. Clearly, what was done with there was a double line tunnel. Clearly, what was done with respect to mixed design or durability and secondary lines to tackle aggressive sewage gas. That's what it was there for. It was there to put in as hydrogen sulfide protection. If I'm honest, I've got to be careful what I say. I hope nobody watches this and doesn't agree with me. But to be honest, I think what I would have prepared to have done, or what I would have liked to have done, is our segments were whatever they were, 275 thick. I forget the thickness, but we had to go from 7.8 to 7.2 diameter. So that is another 300 millimeters on thickness. What I would have preferred to have done is built a segment maybe 500 millimeters thick, so you've got that extra thickness for durability, but cast or had it thinner, by the way, as well, and because there's some structural properties to the secondary lining as well, particularly where the drop shafts were. There was this all kind of water hammer problems, and wearing out. But, you know, there's nothing new with buying segments where we've got a plastic liner cast into them. And, you know, the thickness of that liner could have been, you know, I mean, conventionally we see a lot of these T-lock bars where it's a thin PVC membrane with T-lock things on it so it can get cast in the concrete. You can cast plastic liners on these quite thick. I particularly thought something different could have been done. Anyway, it wasn't. There had to be an in situ liner put inside of it, which was unreinforced. However, what I was looking at before I moved away was to put in, if you like, a TBM inside the tunnel, basically a TBM probably about 30-40 meters long without a cutter head on, like what we call a double shield TBM, what could have gripped inside of the segments and built segments within the segments, and that's what I was looking to do So you've got a tail. So you've got like a double skin shield with like a tail skin. What could inflate a seal, so you could build the segments, grout around them for support, then move forward, like what they call a double shield machine, like you see in hard rock. So it's like a caterpillar. It grips, pulls forward, releases, kind of moves down the tunnel. That's what I was looking to do. I don't think in the long term they went for that. I think there was some issues somewhere. I don't really know the latest of it. Please share the Tunneling and Tunnel magazine where I can post it on here quite easily, or I can send it to somebody. It is something you can share. There's no protection on this link, so I actually always share it within L&T, and I can certainly pass it on to L&T members who are part of your organisation, and maybe they can distribute it. It'd probably be easier than me doing it for you, so I'll do that straight after. What I'll do is, the other one says about Mumbai Metro, Robbins. What I can do as well, I know for a fact the L&T people have got the got May as well, so they can pass you last month's May, and you can have June as well. So that's it. That's all your questions, I think. I hope I answered them to your satisfaction. But thank you for that.